Okay, this is part 3 of log review. And in the last video, remember we talked about using the properties of logs. Well, let's continue to do that with talking about another type of problem. And because we talked more towards the end of the last video about how to solve for a variable inside a log, well, what about how I solve for a variable in the exponent? And if you remember in the past, we have done this, but that was being able to write both sides in terms of the same base. So for example, if we had, let's just quickly do one. If we had something like, 2 to the 2x times 8 times root 2 equals 16 to the x minus 1. I don't know, just making something up. And if I ask you to solve for x, well, I would, and you should always do this first, to see, can I write both sides in terms of the same base? And I notice here, based on the numbers I have, I could write everything in terms of base 2. And that's what I would do. So I would do 2 to the 2x times 2 to the third times 2 to the 1/2 equals 2 to the 4th to the x minus 1. And then multiplying with the same base gets you to addition. So it would be 2 to the 2x plus 3.5 or plus 7/2 equals 2 to the 4x minus 4. And once you have a single base on one side and raised to an exponent, you set the exponents equal to each other because that's the only way this is going to be true. Okay, so I'd have 2x equals 7/2 plus 4 is the same as 7/2 plus 8/2. So 15/2 equals 2x. And if I divide by 2, I get x equals 15/4. Well, that's nice when that happens and that works out, that I can write everything in terms of the same base. Most of the time it doesn't. So that's when logs come into play. So what instead, I had something like this. Say I had, and I said solve for x. Whoops, erase that. And again, let me just make something up. Say I had 2 to the x times 3 to the x minus 1 equals 5 to the, just 3x. Actually, let's make it a little more interesting. 3x minus 2. Okay, so definitely not writing both sides in terms of the same base. So the other kind of the new strategy we learned that in order to get the exponents down, I can take the log of both sides. I tend to take the common log of both sides. You can take the log of any base of both sides. I tend to take the common log if there's no base e. If there's base e, I take the natural log of both sides. So taking the common log of both sides, and remember, you can't take the log of individual terms. It has to be an entire side. So I'm taking the log of the entire side. Okay, and then on the, why does this help me? Well, on the left, I notice I have multiplication, which I'm going to split out by addition. On the right, I only have 5 to the 3x minus 2. Well, the 3x minus 2 can come out in front. 3x minus 2, log 5. Notice I put that parentheses around it because the 3x minus 2 is all multiplied by the number log 5. And keep in mind, log 5 is just a number. It's an irrational number, but it is a number. On the left side, these exponents can come down. Again, putting a parentheses around the exponents if it's more than one term. Okay, so remember the goal here is to solve for x. So I've got to get the x out of those parentheses. So I have just logs of numbers here. So like with if you had a number outside the parentheses, you would just distribute. Same here. So plus log x, I can't speak. I'm going to put the x out in front so it's not confusing. So plus x log 3 minus log 3 equals 3x log 5 minus 2 log 5. And now, again, the goal is just to isolate x. It's not going to be pretty necessarily, but we want to get it in a form that I can just put it into my calculator and actually find the decimal approximation maybe of what this is. Let's get everything with x on one side and everything that does not have an x on the other side. So I'm going to bring the x's to the left. So that means I have to bring the 3x log 5 over. And I'm going to bring the log 3 to the right, and that will join the minus 2 log 5. And in order to isolate x, I'm going to factor it out. Plus log 3 minus 2 log 5. And only one last step to do is to isolate x. I'm just going to divide by that whole log business. So log 3 minus 2 log 5 divided by log 2 plus log 3 minus log 5. Minus 3 log 5. So yeah, could I write this differently? Sure. I mean, I could certainly use the laws of exponents to simplify this right side to make it single log on top and a single log in the denominator. Do I have any interest in doing that? Not really. Because you know what? I was just looking to isolate x, and right now I could just plug this into my calculator and get a decimal approximation. So I'm good with that. So again, that's another type of problem when you're solving for a variable in the exponent and you can't write both sides in terms of the same base. Take the log of both sides and then just be careful with your algebra. All right, let's go back to doing, let's go back to talking about the change of base. So I want to do a couple problems there, which, because again, it is powerful to be able to use this. So let's say let log base b of c equal x. And let's say find the following in terms of x. Okay, so what if I gave you something like, trying to see if I start easy or if I do it a little bit more complicated. Let's do complicated. What if I said find log base log base c of c squared b. And again, your answer has to be in terms of x. Okay, so, first thing I'm going to do is maybe easier to break this up using multiplication goes to addition. So I've got log base c of c squared plus log base c of b. Or I've got 2 log base c of c plus log base c of b. Well, log base c of c is just 1, so that's helpful. 2. Well, I know log base b of c, but I don't know log base c of b. But if I want base b, well, let's just do it. Remember, the change of base says if I have some random log base b of m, I could make it any base I want. I could make it log base, let's just call it base z of m over log base z of b. Well, let's do that here. We want base b because we know log base b of c. So this is going to be plus log base b of b over log base b of c. So look at that. It worked out because why did this work out? Well, log base b of b I know just to be 1. And log base b of c is what we were given. So again, if the base isn't what you want, use the change of base to make it what you want. Okay, let's do something. I'm trying to think of another good one here. How about, what if I said find So that's the 1. Let's find log base, I'll do base b to the 5th, why not, of c to the 3rd. Okay, so let's try this here. And notice here that, again, do I want a base of b to the 5th? No, I would like a base of b. So let's just make a base of b. So this is going to be log base b of c to the 3rd over log base b of b to the 5th. Well, now this is helpful because if I bring the 3 in front, and then I bring the 5 in front, I just, log base b of c is x, so I just have 3x over 5, log base b of b is 1 over 5. So change of base can be fun. Again, you just have to think, okay, how can I don't know, if I don't know something and I want a different base, we'll use the change of base to make it a different base. Let's just do a few more of these here. Again, thinking about the change of base. So I love log problems because they're like little puzzles. And sometimes you just have to try something and you maybe don't know if that's the right way, but just try it. So you've got a lot of tools to use. So what if I said evaluate? So tell me what this ends up equaling. 3 to the log base 9 of 18. Oh boy. So so one thing I realize, or hopefully you realize, is if this were 3 to the log base 3 of something, then I could do it because a function composed with its inverse, you get out what you put in. But the fact that these two are not the same doesn't make me super happy. So let's make them the same, again, using the same change of base. So actually, let's backtrack a little bit. Say you didn't even think this. That didn't even come to mind, which is totally understandable. If you're totally stuck, and think about changing it to the different form. So what do I mean by that? Well, right now, yes, there's a log present here, but overall, we're in exponential form. We've got some base raised to an exponent, which just happens to have a log in it, but it is in exponential form. So I'm going to just set it equal to some random x. So I'm trying to see what this output is. What does this equal? What is x? Well, let's change it to log form. So log base 3 of my answer equals my exponent. Now, going back to what I was talking about before, how would I like to solve this? Well, if the bases were the same, I would just set the insides equal to each other and be done with it. Sadly, they're not, but change of base is such that let's just make them the same. So, and let's pray it works out. So I'm going to keep this left side the same, but let's rewrite this right side in terms of base 3. So this is log base 3 of 18 over log base 3 of 9. Okay, this is actually looking a little bit more promising. I'm not sure if you see it yet, but there is something I can simplify. Log base 3 of 9 is 2. So I've got log base 3 of x equals log base 3 of 18 over 2. Okay, not exactly what I want just yet, but again, if I have a single log on each side, which I'm now getting at, they both have the same base, but I can't have anything outside the log. So let's just rewrite the right side as this is the same as just at 1/2. And why did I do that? Well, anything in front of a log can then be brought up as an exponent. So log base 3 of x equals log base 3. If I bring it up as an exponent, it's just root 18. Now I'm in a good place because the only way this is true is if the insides are equal. So x equals the square root of 18, or x equals, if I take out 9 is 3, x equals 3 root 2. So that's a cool problem. again, utilizing this change of base. Do one more, and then we'll call it here. All right, so again, let's evaluate. Think about something like log base 16 of 81 minus log base 2 of 3. Separate logs. It would be nice if I can bring them together, but they are different bases right now. But I do know something's relatable to the bases. So 16 is a power of 2. So let's see if I can use the change in base to make these the same base. And then I can use my properties of logs. So on the left, I'm going to change this. Instead of base 16, I'm going to use base 2. So this is log base 2 of 81 over log base 2 of 16. And I'm going to keep log base 2 of 3 the same. Log base 2 of 16 is just 4. So I'm going to write this as 1/4 log base 2 of 81, not equals, minus log base 2 of 3. And then let's bring the 1/4 up as an exponent. And the 4th root of 81 happens to be 3. Okay, so now, oh, interesting. I've got log base 2 of 3 minus log base 2 of 3, which is just 0. So change of base, very powerful. So don't forget that when you, as part of your toolbox, when you are solving problems involving logs.